Hey, it's Mr. Shrum, and I am back with another tutorial. Last time we learned about Newton's three laws of motion, and today we're going to look at the first. And the first law deals with mass, inertia, and equilibrium. So let's get into that. So for the introduction, I want you to picture a pool table. Right, you have the white cue ball, you hit it with a cue stick in order to hit other billiard balls into the correct hole or socket or whatever, right? Now that cue ball sits in the middle of the table and it's going to stay there at rest until you pick up your cue stick and hit it. And when you do hit it, the ball moves in a straight line and it'll continue to do that until it hits the cushion of the pool table, hits another ball, or sinks into one of the pockets. The cue ball follows Newton's first law of motion. His first law states that an object at rest stays at rest, and an object in motion continues to be in motion with the same speed and in the same direction, unless it is acted upon by an unbalanced force. So let's consider another scenario. A meteoroid, a little tiny meteor, speeding through space, moves in a straight line until it reaches the surface of Earth. What keeps a meteoroid moving? Can objects move in the absence of force? And does the meteoroid also follow Newton's first law of motion? Well, let's learn a bit more about this law and its application. This law is also called the law of inertia. So, like we said, the cue ball will stay at rest unless it is hit with some force, and it continues moving until it's stopped by another force. The motion of this ball and any object will continue in its present state until an external force acts on it. Things want to do what they're doing unless there's a force acting against it. So from the pool ball example, you can infer objects resist change in their state of rest or motion. And that resistance is called inertia. We normally think of inertia as it applies to two everyday situations, being at rest and being in motion. Imagine yourself standing in a bus that is stopped. Suddenly, the driver pushes down on the gas pedal and the bus lurches forward. So you find yourself falling backward. And this is because your body was at rest and your body wanted to stay at rest. When the bus moved forward from the acceleration, but your body remained at rest, and then you fell backward. On the other hand, if you are standing in a moving bus and the driver applies the brake suddenly, you fall forward. That's because your body is in inertia of motion. The brakes force the bus to stop, but your body continued to be in motion. Okay? We now know that all objects resist any change in their state of rest or motion. But do some objects resist change more than others? If so, what factors influence this resistance? Let's consider an example to get answers to these questions. Say you push or apply a force to accelerate a small toy car on a frictionless surface. If you apply the same force to a bigger toy truck that is twice as heavy, which one will be moving faster after the push? The smaller one, right? We know that in general, lighter objects need less force to accelerate or change their velocity than heavier ones. Imagine pushing a toy car versus a real car, right? That makes sense. This everyday example illustrates that the inertia of different objects is influenced by their mass. we define the mass of an object as the amount of matter in the object. And the SI unit of mass is the kilogram, kg. So in this question, which statement is true if the mass of object A is twice that of object B? I would say object A requires half the force. That's not the case. If object A has more mass, twice the mass, then it requires more force than B, not less force, okay? Newton's first law of motion describes objects when they are at rest and when they are in motion. It also describes the force acting upon them. Let's translate some terms related to the first law of motion into mathematical form. When an object is at rest, it has zero velocity, v equals 0. It's not going anywhere. It's at rest. When an object is in motion, it's not at rest. So the velocity is not 0. So if it's at rest, velocity is 0. If it's moving, velocity is not 0. And we say that by v does not equal 0. Once that object is in motion, it continues to move in a straight line with the same speed unless acted upon by an unbalanced force. Before it is acted upon, the object is said to be in motion with a constant velocity, v. The only thing that will change the velocity of an object in motion is an unbalanced force, such as the friction it encounters. When an object stays at rest or moves with a constant velocity, all the external forces acting on the object are balanced and the net external force is 0. This relationship is expressed as the summation of F equals 0. Note that a net force is the vector sum of all forces acting upon an object. So, whether an object is at rest or in motion, an object that stays at rest or moves with a constant velocity, all of the forces on it are balanced and the net external force is 0. So it wants to stay in its current mode, whether it's at rest or moving at a constant speed. We know that force is needed to accelerate objects, to change the speed of objects, or to change their direction of motion. Force is also required to pull objects together or push them apart. Forces, as you may recall, can be generally classified as contact forces or field forces. Remember, contact forces like friction, tension, spring, air resistance act on objects through direct touch. They have to make contact to force another object. But field forces, also called fundamental forces, act on objects from a distance without touching them. Remember these 4 basic field forces. Gravitational force. Gravity is responsible for holding all of the planets in their respective orbits around the sun. It's the force of attraction between any 2 masses. Electromagnetic force. That's the force of interaction between charged particles. Like charges that are the same, repel each other while opposite charges attract. The strong nuclear force occurs between a pair of protons, neutrons, or a proton-neutron pair in the nucleus of an atom. So at the very, very small scale, at the nucleus of an atom, there's a strong and weak nuclear force. And the weak nuclear force exists between subatomic particles in the nucleus. It's much weaker than the strong nuclear force because it's called the weak nuclear force. And even though it's weaker than the strong nuclear force, we can still see how it affects atoms and how it keeps the nucleus together. So if you guys like football, let's consider that for an example. Here's a video, and then we're going to answer the following questions. How does the mass of a running back play a role in his inertia of motion on the football field? If the inertia of a defensive player is greater than the player carrying the ball, what can the ball carrier do to avoid always being tackled? So let's check this out.
Whether it's a running back breaking through the secondary or a wide receiver on a foot race for the end zone, most defensive players in the NFL have a single goal in mind: to get downfield as far and as fast as possible.
You're thinking, wow, I've got to get from A to B within a certain time frame, and I can't let this guy throw me off track. So it's kind of like a chess match at that point in time. It's the battle to see who's the toughest.
Defenders, on the other hand, have a different goal: to stand in the way of the offensive player and stop his forward progress.
When you come in and making the tackle, you've got to come in and you've got to stop him right there on the dime.
Who wins this epic battle between the ball carrier and the defender? Newton's first law of motion helps supply some answers.
Newton's first law says that if an object is at rest, it requires an unbalanced force to make it not be at rest. Or similarly, if an object is in motion, it tends to stay in motion in a straight line at a constant velocity unless an unbalanced force acts on it.
In football, we see unbalanced forces whenever one player exerts a force on another and causes him to change his direction and or speed.
So imagine that a quarterback is just taking a snap from the center,
And a lineman gets free from the opposing team is coming from the other side. And when they collide, you can see an unbalanced force acting on the quarterback, driving him across the field in the direction of the charging lineman. That's about as unbalanced as it gets.
In physics, a player's natural resistance to that unbalanced force is something called inertia.
On the football field, you can think about inertia as being a running back who's already in motion, doesn't want to change the fact that it's already in motion. So it's going to take some external unbalanced force, i.e. a defensive player, to stop that running back.
Consider former New Orleans Saints running back Deuce McAllister, who at 6'1", 231 pounds, used his inertia when running to make it hard to tackle.
The size of the player is important to the concept of inertia because higher mass means more inertia.
But a player's mass is different from his weight. Mass is a measure of how much matter an object has, while weight is a measure of how strongly an object's mass is attracted by gravity.
So, for example, a body on Earth would have the same mass as that body on the moon, but it would weigh less on the moon because gravity is less on the moon than it is on Earth.
NFL players with more mass have more inertia and are harder to move off their path. This concept even works on quarterback sneak, when a quarterback uses the combined mass of his entire offensive line to gain a yard or two.
If you've got an offensive line that can overpower the defensive line, that's just what you do. You get on their hip and you just fall. Just ride that wave forward.
In the NFL, whenever players go head-to-head, it's Newton's first law of motion that helps determine who will win the battle of the gridiron.
Okay, so that is a cool video showing how even in sports, Newton's first law of motion can be applied. Okay, So I will have to leave here, but I will pick this up in the next tutorial, and I will see you later. Bye-bye.